These are the notes for AP Calculus on the topic of integration by parts continued. So remember integration part that comes from the product rule, but we have to assign one part of the integral to f of x, and that's the part that usually has a simpler derivative or simplifies more with the derivative, and it's that one part of the integral to g prime of x, that's the part that usually integrates more easily, or at least doesn't get too complicated by integrating. So here we've got x times secant of 2x squared. So in this case, probably the easier thing that simplifies more is x, so that's probably a good idea to set that equal to f of x. And another reason why you can see why that would work well is because if you set f of x equal to secant squared, it's going to involve the double chain rule and get way too complicated in order to integrate. But if we set g prime of x equal to secant squared, it actually doesn't get more complicated. It's one of the trig integrals there, so it actually gets a little simpler. So that's another way to tell it's going to work out better this way. Because remember, the idea is you want this integral here that we end up with inside integral to be simpler than the integral here, the one we're starting with. The idea is to make it one that's easier to integrate than what we started with. All right, so then we take, remember the derivative of this one, of f of x, that's f of x, the derivative of x is just 1, that simplifies nicely. And then we integrate this one to get back to g of x. So when you integrate secant squared, remember you get tangent, so the derivative tangent of secant squared, the 2x stays inside there. However, remember we have to use the shortcut for u substitution here. Because the function inside is 2x, we normally say u equal to 2x, the derivative would be 2, so you have to divide by 2. So I can just put it out in front as 1 over 2. So then, this is an indefinite integral. So you can see this integral would equal f of x, which we have as x. Remember, these are the original functions, not the derivative, so x times g of x, which we just figured out, is 1/2 tangent of 2x. And then minus the integral the two that we found is whatever, f prime and g, these two right here. So it's going to be 1 times 1/2 tangent of 2x. Times dx. So notice it is a little bit simpler of an integral here because now we don't have any more x's there. We have a trig function and just a 2x inside, and there's not a trig function squared. So it's going to get a little simpler here. So let's work on this integral, and this part will just go out in front at the very end here, the x 1/2 tangent of 2x. That part's already integrated. That's why it's integration by parts. We integrated part of it, but we still have to integrate the other part of it. So what you can do here is a couple things to make it easier to integrate. You can pull out the 1/2 along with a negative sign. That's a constant out in front. And then in order to integrate tangent, that doesn't fit any of our trig integrals. So to make it easier to integrate, what we can do is rewrite tangent using sine and cosine, because those will work with more often. So tangent, instead of tangent of 2x, we can write that as sine of 2x over cosine of 2x. And by doing so, now we can integrate by using u substitution. You could try setting u equal to 2x, the function inside, but then you just have sine of u over cosine of u. That would still not be simple enough to integrate. So this is the one where we'd set u equal to the entire denominator. But notice the derivative of cosine 2x is not a constant. So this is not one you can use the shortcut on, like we did for secant 2x squared. So here you just do traditional u substitution, where there's our u value, and then you take the derivative of that using the chain rule. So du dx would equal derivative sine. So our derivative cosine is negative sine. But then using the chain rule, you have to multiply by the derivative inside function times. So then dx, you multiply by dx and divide by that, ends up equaling negative 2 sine, oops, sorry, du divided by this, divided by negative 2 sine of 2x. And you can see that's going to work out nicely because when we substitute that in for dx, that's going to help us remove the sine of 2x. So let's see what we've got now. We've got negative 1/2 on the outside. Integral of sine of 2x over u, that u equal to cosine 2x. And then dx we can replace with u over negative 2 sine 2x. So then you can see the sine of 2x's reduce out, which is what we wanted, get it all in terms of u. You can pull out the negative 1/2 here, times the negative 1/2 that's already out there, which gives you positive 1/4. And then notice all we're left with is the integral of 1 over u. Integrate. So when you integrate 1 over u, you get natural log absolute value of u, and then we'll have the plus c. And then don't forget, on these indefinite integrals, remember you have to substitute u back in. So we'll take our cosine of 2x, which is what u is equal to, and substitute right back in here for u. So for this part of the integral, we've got 1/4 natural log absolute value cosine of 2x plus c. And then just don't forget to bring down the first part of this integration by parts problem. You could bring the 1/2 out in front, so just 1/2 x times tangent of x. Remember, this was a positive one. So there would be your final answer for the indefinite integral. So that was an indefinite integral. Now, let's take a look at one with lower and upper limits, a definite integral. Okay, so again, we have to choose which to set equal to f of x and which to set equal to g prime of x. So this one's a little trickier in some ways. F of x is the one that simplifies better. It's easier to take the derivative, so you can either take x cubed, which simplifies to be 3x squared, or derivative natural log of x is 1 over x. So it looks like either one is pretty easy to take the derivative, but integrating, notice, when you integrate x cubed, you'll get x to the 4th over 4, but an integral of natural log of x, that's not one we have a formula for. So, in this case, it'll be easier to set f of x equal to the 1. Natural log of x kind of determines it here. When you have a natural log in there, it's usually set it equal to f of x because it's easy to take the derivative. And then the other part, g prime of x, will be equaling x cubed. Then we take the derivative of natural log of x to get f prime of x is 1 over x. And then we integrate g prime to get back to negative x. Using the power rule of x. And again, we don't worry about that plus c till we're all done with the problems of integrating by parts. So this integral is going to equal f times g, so natural log of x, times g of x we just figured out is x to the fourth over 4, minus, oh, and this is a definite integral, notice, so this part is the part that's already integrated, that's going to be evaluated from 1 to e, and then minus the integral from 1 to e of the two we just found, 1 over x, or f prime of x times g of x is x to the fourth over 4. So we'll work on this part once we get this other one integrated here. Just erase it, so it's probably a 1. Yeah. So notice we can simplify this. We can pull out the 1/4 out in front. As a constant. And then notice the x and the x to the fourth simplify. So x goes into the, cancels out one of those, so you end up with x cubed inside of our integral. 1e. All that's left here is x cubed. Which now we can integrate that, so we have negative 1/4 here. When you integrate x cubed, you get x to the fourth over 4. 1 to e. And before you substitute an e in 1, you can pull out the 1/4 times the negative 1/4 that's already out there. Negative 1/16. And then all that's left inside here is x to the 4. And I'm just going to bring this one down here and simplify a little bit as we go. So we can do this whole definite integral all at the same time. I just think it's a little easier that way. So you can pull out the 1/4 on this one. And usually the x to the fourth would be written first. And then times the natural log of x. So I'll write x to the fourth and then natural log of x. All right, now we can just evaluate each of these. So we've got 1/4 on the outside here. And then we substitute in e. You'd have e to the fourth times the natural log of e minus 1 to the fourth times the natural log of 1. And on this one, you'd have minus 1/16. Substitute in e, you get e to the fourth minus 1 to the fourth. Natural log of e, remember this is saying e to what exponent is e? That's 1. So that, and natural log of 1 is 0. So that's going to wipe out the whole term here. So this first term we just have 1/4 times e to the fourth, because it's 1 times e to the fourth. And then here, if we distribute this negative 1/16, we have negative 1/16 e to the fourth minus 1/16. Whoops, it's actually positive because of the negative cancel out the negative times the negative, so it's positive 1/16. My bad. And then you could leave it like that, or notice you can combine, these two are like terms. This is the same, 1/4 is the same as 4/16. So you could combine it to be 4/16 minus 1/16 is 3/16 e to the fourth plus 1/16. You could write it like that. Or since they already have a common denominator, you could also just write it as a single fraction, 3 e to the fourth plus 1 all over 16. Either way is fine. All right, let's take a look at one more that's just a little different context. It requires integration by parts. So this one is a particle moves along the y-axis, and we're given its velocity function, v of t. At time 1, the position of the particle is x of 1 is 5. Sorry, that should say y of 1. Typo there. This is moving on the y-axis. Write an expression for the position of the particle y of t. So to go from velocity back to position, you have to integrate. So y of t, that's how you know you need to integrate this velocity. It's going to be the integral of t squared natural log of t minus t squared minus dt. So there's a couple different ways you can handle this one. You could split it into two separate integrals to start with, because t squared is pretty easy to integrate, and then use integration by parts on the t squared natural log of t. That would be fine. But because they both have t squared, it's actually probably a little bit more efficient, although you don't have to do it this way, is to factor out that t squared. And then notice what you'll be left with is just the natural log of t minus. And then we don't have to split the separate integral because we can use integration by parts right there. The only thing that's a little weird is we don't have f of x and g prime of x, we have f of t and g prime of t. So kind of like the last one, remember when you have a natural log, it's easier to take the derivative of this than to integrate it. So that's why we're going to set f of t in this case equal to natural log of t minus 1, and g prime not of x but of t equal to t squared. So then we can take the derivative of this one, derivative f of t, f prime of t is just 1 over t, derivative negative 1 is 0. And when you integrate g prime, you get g of t, you get t cubed 3. So now we can rewrite this one. F times g, so the natural log of t minus 1 times g is t cubed over 3 minus integral of the two we just found, f prime and g. So that's 1 over t times g is t cubed over 3. And then we can work on integrating this one. You can simplify it, notice. You can pull out the negative 1/3. And then you can simplify it. T here reduces this to t squared, so all we're left with integrating it to t squared. And then we can integrate this one. We get negative 1/3. When you integrate t squared, we get t cubed over 3. And then we can put a plus c. And so what we've got now for y of t, position function, remember, was equal to this integral. This first one, you could distribute it out or leave it in this form here. I think it might be a little simpler in this case to distribute it because we're going to have another term over here we might go to combine with. So either way is fine though. So we'll have t cubed over 3 natural log of t minus t cubed over 3. And then if we simplify this term, it's going to be minus t cubed over 9 plus c. So the only thing we don't know is what is that unknown constant, and that's where this point comes in handy. Notice this is our t value, and this is our y value. So we can see y is 5, so we can put in 5 for y of t, and put in 1 for all these. So this would be 1 cubed over 3 natural log of 1 minus 1 cubed over 3 minus 1 cubed over 9 plus c. So there's that natural log of 1, which again is 0. So that wipes out this whole term. E to what power is 1 is 0. So then what we're left with is 1/3 minus 1/9. So you can get a common denominator for those. This is like negative 3/9, being multiplied by 3 over 3. Minus 1/9 is negative 4/9. So you have on the right side of the equation, you have negative 4/9 plus c. And then the 5, if you get a common number, multiplied by 9 over 9, is the same as 45 over 9. And then add the 4/9 to both sides. Gives you c equals 49. And now we can substitute that right in here for c. So our final answer, I'll just write it up here. A little more room here, is y of t equals, we've got t cubed over 3, natural log of t, minus t cubed over 3, minus t cubed over 9, and we just figured out c is a positive 49 over 9. So there's our position function. Sorry about that. So we went velocity back to position by integrating, and we used this point here that they were given on position, and we needed that, otherwise we wouldn't know what that unknown constant would have to be. You plug that in after you integrate with integration by parts in this case to solve for c. And that concludes the notes for AP Calculus on the topic of integration by parts continued.